Alright, so the last thing I want to talk about here is Coulombs Law. And this should work very similar to gravitation. The only difference is when we talk about gravitation, mass is positive, and it's always positive. Gravitation is always attractive. It's never repulsive, so you can't push something away using the force due to gravity. But because charge can be both positive and negative, the electric force from a charge can either be repulsive or attractive based upon whether the two charges are both the same charge or whether they're opposite charges. So Coulombs law has a very similar shape to Newton's law of gravitation. So we're going to calculate an electric force. There's of course a constant. We often refer to this as Coulomb's constant. And K can be rounded to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Rather than having two masses, now we're going to have two charges. And these are absolute value signs here, so we have charge 1 and charge 2. Because whether the force is positive or negative is going to depend upon your coordinate system. Remember, force is a vector, so it's going to be whether the charge is attractive or repulsive within the coordinate system you've set up. So Q is going to stand for charge in coulombs. And then divided by r squared, where r is the distance between the two charges. So, say we have a system like this, where we have a positive charge, a negative charge, and a negative charge. Let's call this one 1, 2, 3. So this is going to be the distance between R1 and 2. This is going to be the distance between R2 and 3. So say I want to find the net charge on charge, not net charge, where's my eraser? Net force on charge 2. Now one of the charges in our formula is going to experience the force, one is going to exert the force. So if I want to find the net force on 2, I need the net force of 1 on 2 and the force on 2 due to 3, so 3 on 2. So the next thing I need to do to decide is it positive or negative? So we're doing everything perspective of this particular charge right here. So 1 on 2, these are opposite charges, so there's going to be attraction, so it's going to get pulled this way. So this is going to be negative down here. This one here, since they're the same charge, is going to push this one away, so it's also going to be this way. So this one is going to be negative. So we would finish filling this out by, we have our constant, charge 1, charge 2. Notice this is still in absolute value signs. And then R1, 2 squared. And then over here, we're still going to have charge 2 here, but now we're going to have charge 3 exerting the force. Also still negative. And then the distance between 2 and 3. So one charge exerts the force, one charge experiences the force. So because I'm finding the force on 2, the charge of 2 needs to be in both. And notice their absolute value signs. So when if I give you a number for the charge, you would discount the minus sign for charge 2 and 3. Whether the force is positive or negative depends upon, from whatever charge of interest you have, is it being pulled to the negative direction or pushed in the negative direction, or pulled in the positive, or pushed in the positive. So we have to remember that force is a vector. So in this case, everything was in the same plane, but if we have a scenario like this, the force between these two is in the y direction, but the force between these two is in the x direction. So we can't forget about the concept of vector addition, where you'd have to find the y component and the x component and then use Pythagorean's theorem to find the magnitude. So do not forget that force is a vector.